Okay, this section is really important because we're going to talk about arc length and especially this new concept called curvature, which is a measure of how much a curve is bending as you move along the curve. Arc length isn't too bad. We've already seen arc length in chapter 10, I believe, when you have parametric curve given by x equals f of t, y equals g of t, and z equals h of t. The length of the curve from A to B is given by this formula. Well, isn't a vector function really the same thing as a parametric curve? So this shouldn't be too surprising. For example, suppose you wanted to find the, if you're given a vector function r of t equals sine t, cosine t, and t, and you wanted to find the length of the curve from 0 to 2 pi. So you're starting here at t equals 0, and you're bending around once, and you come back to the same at t equal 2 pi, you're directly above this point, 0, 1, 0. So I want to find the length of this curve. Okay, so all you have to do is take the derivative of the component functions, right, and square them and add them together. Something very nice happens. This is a very simple problem because when you take the derivative of the components, square them, add them together, and take the square root, inside the square root, don't you get cosine squared plus sine squared, which is just 1? So everything just turns into square root of 2. Boy, that's nice. It usually doesn't happen that way, does it? When you integrate radical 2, you get radical 2t, evaluate between 0 and 2 pi. So your final answer is 2 square root of 2 pi. That's nice. Here's an observation that actually comes up. Isn't it true if this is your vector function, then the magnitude of r prime is this? Remember what you do? You find r prime, which would be the derivative of each one. To find the magnitude of it, you just square them and add them together and take the square root, right? Well, you should have noticed that the magnitude of r prime is exactly the same expression and the integrand, right? This is exactly what this is the magnitude of r prime. So the arc length could also be written as s equals the integral from a to b of the magnitude of r prime. And you will see this later. We will use this fact. All right. Another thing that's kind of interesting is you could have an arc length function. Think of s of t as the arc length so far. Suppose you start up at t equal a and you move along the curve until t equals s, and you want to find the length of the curve. Notice I'm not using t here as the dummy variable. You're not supposed to use the dummy variable the same as the limit of integration. But you do notice that this could also be written as the magnitude of r prime of u. Isn't that what this is? That's what we just said. So the arc length function, think of it like this. You start at some point a, and you move along the curve at some t value, it'll tell you the length of the curve that you traveled so far. It's the distance you've traveled, isn't it? Anyway, by the fundamental theorem of calculus part 1, what is ds dt equal to? See if you can tell me that. What is ds dt equal? ds dt equals, it equals the integrand evaluated at the upper limit. So ds dt, the rate at which the arc is changing with respect to time, is the magnitude of r prime. That's a nice little fact that we're going to use in just a minute. Okay, let's define the curvature now. The curvature of a vector function is a measure of how much the curve is bending as you move along the curve. Specifically, it's the magnitude, it's the rate of change, I should say it's the magnitude of the rate of change of the unit tangent vector with respect to arc length. Now the reason why we use s instead of t here is because depending on your parameterization, you might get different, you might be moving along the curve at different rates of speed, so it would come out differently depending on your parameterization. But if you're measuring arc length, then it doesn't make a difference how you parameterize it. It's how far you move along the curve. So this is kind of a standard way of doing it. But it does work. This might help a little bit. By definition, dTds is the limit of the difference quotient, right? So if delta s is small, it's the approximately equal to the difference quotient. So let's just look at t of s plus delta s minus t of s. Suppose, first of all, that you're moving along a straight line. Okay, so suppose you've gone a distance s, on arc s, and then you go an additional distance delta s. So this would be the tangent line at s, this would be the tangent line to s plus delta s. Notice they're both exactly the same because they haven't curved. So when you take t of s plus delta s minus t of s, you would take t of s when you take minus it, don't you reflect it? And it would be minus t of s would go this way. And then when you add it to this unit tangent vector, don't you get 0? Because this will be opposite direction and equal to this, so you get 0. Which is what it should be. The curvature should be 0 if you have a straight line. However, if you have a curve that bends a lot, at here you might have a unit tangent vector going this way. If you go an additional delta s units, the unit tangent vector may be way over here. So when you take the difference between this vector, t of s plus delta s, minus t of s, you would move this. Remember, when you take minus a vector, you multiply by -1, you add the opposite. So this vector would be going this way. When you add it to this vector, then you get a long vector, right? And the absolute value would be positive. So clearly you wouldn't get 0. It would be pretty big. The more these vectors differ in the direction, the bigger the curvature would be. So when you divide by delta s and take the limit as delta s goes to 0, you know that the curvature would certainly not be 0. Anyway, that's nice. That's really nice. It's a good concept, but it's actually very hard to compute. We don't generally use that formula to compute the curvature. Here's what we do. Let's suppose that the arc length can be written in terms of t, and we could actually show that there's homework problems where they do that. Suppose the arc length can be written in terms of t, and then the tangent vector function can be written in terms of s. So if you apply the chain rule, dt, derivative of tangent vector with respect to t, by the chain rule is equal to the derivative of the tangent vector with respect to s times ds dt. Now remember, the curvature has to do with dt ds, so if we solve this for dt ds and take the absolute value, dt ds is dt dt over ds dt, so you take the magnitude, the magnitude of ds dt is positive as long as you're moving in the positive direction, so that you don't need absolute values here. But here, this is the magnitude of t prime of t, and we already said earlier ds dt is the magnitude of r prime of t. So this would be a nice way to compute the curvature. All you need to do is for a vector function, compute r prime, compute t, and compute t prime, and you could find the curvature. Suppose we're moving around a circle of radius a, and I want to compute the curvature. What do you think? Do you think the curvature would be constant if you move around the circle? I bet it is. Anyway, remember the curvature is given by this. So first of all, we compute r prime, take the derivative, and the magnitude of r prime turns out to be a. You see that? And then we have to compute t. The way you compute t is you take the magnitude of r prime, or I should say you take r prime divided by its magnitude. That's the vector t. So you get this. Now what do? You got to take the derivative of t, and you get t prime. So this is part of it. This would be t prime. And we have to find the magnitude of t prime as well. So the magnitude of t prime it's easy to see that it's 1, isn't it? So put it all together. The curvature is just the magnitude of t prime, which is 1, divided by the magnitude of r prime, which we decided was a. So the curvature for our circle is 1 over a, which makes pretty good sense, because the bigger the circle, the smaller the curvature, closer to 0. Smaller the circle, the smaller the radius of the circle, the bigger the curvature. It turns out there's even an easier way to compute the curvature, so you don't have to mess around finding t. We're not going to prove this, but we did it in class, or we will do it in class, that you can show that this is equal to this. So the easiest way to compute the curvature, if you have a vector function, is just compute r prime, compute r double prime, and look at the cross product of those, and look at the magnitude of the cross product, and then divide by the magnitude of r prime cubed. So let's do that. So we first of all compute r prime, we get this. The magnitude of r prime, we've done this before, I believe, we get square root of 2. Now we compute r double prime, we get this. And then we want to compute the cross product of r prime with r double prime. So you get this. Now all we have to do is find the magnitude of that cross product. The magnitude of the cross product, isn't it going to be, also it's going to be square root of 2, it turns out. The magnitude of this vector is the square root of 2. So all you have to do is take the magnitude of the cross product divided by the magnitude of r prime. So we get this. The curvature is square root of 2 divided by square root of 2 cubed. Don't forget to cube this. So that turns out to be 1/2. Interesting, huh? There's yet another way. Let's see. I think this becomes number 4. If you have a plane curve in R2 in the xy plane, and you want to find the curvature of, say, a function y equals f of x, couldn't you think of it as a vector function where x is the parameter and the z coordinate 0? And that's true with any curve in the xy plane. You could always think of it as a curve in R3 by just making the z coordinate 0. Anyway, so this is your vector function where x is the parameter. I'm not going to show this. It's pretty easy to show. It's very easy to show that you could show that when you plug this vector function into this form, and you just get the absolute value of f double prime over the absolute value of 1 plus f prime squared to the 3/2 power. Now think about that. The curvature, shouldn't that have something to do with f double prime? The concavity. So this form would kind of makes sense. Anyway, so let's do that. Let's find the curvature of f of x equals x squared. You would find f prime, f double prime, and then all you have to do then is take the absolute value of f double prime divided by 1 plus f prime squared to the 3/2 power. So there it is. So this is the curvature for y equals x squared. Notice it's 0. When x equals 0, the curvature is 2. And the bigger that x gets, the closer that this gets to 0, doesn't it? As x gets big, this gets close to 0. Interesting, huh? All right, one more concept here. Let's define the unit normal vector. We already talked about the unit tangent vector. So the unit normal vector is kind of like going one step further. You take the unit tangent vector, you take the derivative, and you turn that into a unit vector. That's what the unit normal vector is. I'll show you the geometric interpretation in just a minute. And then the binormal vector is just the cross product of t with n. It turns out the binormal vector is a unit vector. That's not obvious, but if you look at the magnitude of it, isn't the magnitude of a cross product equal to the magnitude of the first, magnitude of the second, sine theta? Well, we do know that t is a unit vector, and we do know that n is a unit vector, so that's 1. But why is sine theta 1? Why are t and n orthogonal? And the answer is, since t has constant magnitude, didn't we just show earlier that it's orthogonal to t prime? And any vector with constant magnitude is going to be orthogonal to the derivative vector. So n is just the derivative of t that's been made into a unit vector. So t is orthogonal to t prime, therefore it's orthogonal to n. So yeah, sure enough, b has magnitude 1. All right, last thing here. We can talk about two planes. Well, first of all, think of it like this. If you have a point P here, this is your point P, the tangent vector is going to be tangent to the curve along the tangent line. The normal vector will be inside the curve, bending inside the curve, the direction of which the curve is bending. And then since B is the cross product of t with n, you would look at a vector orthogonal to t and n using the right-hand rule. The normal plane is determined by the vectors n and b. So t would be the normal vector for the normal plane, right? The more interesting one is the oscillating plane. The oscillating plane is determined by the vectors t and n. So b would be the normal vector for the oscillating plane. If you wanted to find the equation of the oscillating plane, like I'm going to ask you to do now, all you really need to do is find that vector b, right? I want you, at t equal pi over 2, we want to find the equation of the oscillating plane. What you need to do is you have your point, you define the vector b. How do you find b? You find r prime, you find the magnitude of r prime, so this is your vector t. Now you have to find the vector n. The way you find the vector n, take the derivative of t, find t prime, make it into or find its magnitude, and then the n vector is you would divide t prime by its magnitude. So this turns out to be the vector n. Now to find b, all you have to do is cross t and n. You get this vector. So the rest is pretty easy. Now that you know your normal vector for your plane, and you know a point, all you have to do now is dot the dot b with the direction vector for any other point in the plane, and then you dot the dot product. Turns out to be this: x plus z equals pi over 2. Pretty nice, huh? We'll see you later. Bye-bye.